Applied force or tension. Okay, you're gonna have to bear with me for these videos. I haven't had much warning. So these are gonna replace the seminar that we're having on Thursday. Let's talk about applied force or tension. So let's say you apply force through a rope. Okay, here's a rope, and it's attached to a wall. All right, and this guy with his cartoony hands is pulling on that rope. He's got nice collared shirt and cufflinks. He pulls on it. If you pull on it, you picture this as the wall, there's going to be tension in that rope, right? If you pull hard enough, it's going to get taut. And then now if this wall was a block that's sliding along a surface, you see that you could make the block move because you're pulling the rope, and that tension is the applied force to the block. Okay, so it's the same as a push or pull to any object. Okay, so let's just draw a free body diagram. Okay, so you should know these from last year. Free body diagram, most of the time we're just drawing a square, and it's normally on some sort of surface. You can probably guess that those surfaces are going to be inclined, meaning that you just looked at what happens to friction on an incline and force of gravity on an incline. But for now, let's say you're on a horizontal surface. So let's say we've got an object, we pull it at a constant velocity along this horizontal surface. Okay, now let's do some things to it. The applied force is through a rope, okay, which makes an angle of 30 degrees with the horizontal. Draw the free body diagram. Okay, so for grade 12, if you want to picture this, always have some sort of center point to your block that you're going to apply these forces through. So there's the center of this block that's sitting along this horizontal surface. Obviously, what do we know right away? The block has mass, which means there is a force of gravity pulling it down toward the earth that's keeping it on this horizontal surface. Now we say that we pull it at 30 degrees with the horizontal. So you draw in this dotted line, that's the same as this surface here. So I want to go up 30 degrees from that dotted line, and I'm going to pull on it. And this is going to be my force that I apply. So you can either label that Ft for F tension, or you could also label that, if you wanted to, let's erase that, and you could also do F app, force applied. It's up to you. It's not going to make a difference really. Okay, well, what else is happening? You should know this from the last lesson that there's a normal force on this block. Okay, and this normal force acts, well, perpendicular to this horizontal plane. And also, let's say that, go away, this isn't friction, oh, sorry, this isn't frictionless, so let's say there's a force of friction, and that force of friction acts to the left because it's opposite the applied force, right? The applied force is going to make this thing move right, and the force of friction is going to want to keep it from moving that way. Okay, so that's just a standard free body diagram, and we'll use them for all of the 5 examples that we're going to go through. An elevator with a mass of 900 kilograms, so mass equals 900 kilograms. It's accelerating downward at a rate of 1.30 meters per second squared. And what we want to find is what is the tension in the cable. Ft equals, we're going to find that. Okay, so you can just picture that. You have an elevator, there are people in there. Here they are. That's DJ dressed up for Hawaii Day. And then there's cable. Let's say it wraps around a pulley. So you can picture that a mass is pulling on this rope, which is creating tension, or in this cable, which is creating tension in it. Okay, so now we're going to draw the free body diagram for that elevator, and it's just going to be a square. So here is the center of that. What's acting on it? Force of gravity. Force of gravity is acting down. Okay, what's counteracting that? Force of tension. You could put it as F app here if you wanted, but it seems logical to use Ft because it's tension in this case. Again, it doesn't really matter, but I don't know. Ft makes more sense for this one. So, what you know for Physics 12 now is that F net equals the sum of your forces. Okay? F net equals the sum of your forces. F net equals ma. So the sum of your forces equals ma. If you weren't accelerating then the sum of your forces would equal 0. Okay, in this case, we are accelerating. We're accelerating downward at a rate of 1.30 meters per second squared. So you might want to put that off on the side and say that we're accelerating down. Okay, so this thing's moving down. We're going to use this to figure out what to do here, because these are all actually vectors. Okay, if we write out all the vectors down here and take it into account with our picture, then we don't have to worry about putting in all the signs later. Okay, so convention is that up is positive and right is positive, but you know what, when you get into these problems, it's up to you. You can call down positive if you want. It doesn't really matter as long as you stick to, if you're calling down positive, then you better make sure that anything that's going up is now negative. Okay? But for this question, we're going to stick to that because it's probably going to make this simpler. Okay, so some of the net forces acting on this elevator are m times a. And these are all vectors, so let's write out an equation for this to figure out what the tension is. So sum of the net forces equals ma, F net equals ma. We know that. What are some of the forces? Sum of the forces. Okay, well, nothing's happening on the sides, right? We're only looking at up and down. So if you want, for sake of accuracy, we're really just looking in the y direction. Okay? Some of the forces in the y direction. So you have Ft, which acts up. Okay? So that's going to be positive. Okay? And then you have Fg, which acts down. So that's going to be negative Fg. Okay? So notice that I don't have to draw the vector hats on top of this because I've already taken that into account with these positive and negative signs. We could do that for F net as well, right? Up here we're saying, okay, well, you have to look at the vectors, but we could say that F net equals m times, well, A is acting down, so A is a negative. So by making this negative, we don't need the hat on top because we know that we're taking into account the vector because it's going down, which is negative. Okay, so what does this mean? Sum of the forces equals F net, right? So that means that Ft minus Fg equals negative ma. And we're looking for Ft, so let's just move Fg over to the other side. So that means that Ft equals negative ma plus Fg. Okay, and when you're sticking in values, Fg, remember that's mg, and you're sticking in values for a, we've already taken into account that these are vectors. Okay, that's already taken into account. So now we can just put in magnitudes, which should make our life a little bit easier here. So, let's make it actually super easy. Fg is mg, right? So let's rewrite this as negative ma plus Fg is mg. And I don't want to calculate mass twice, so let's factor out m. And you're left with G minus A. Okay, so the tension in this elevator is mass times G minus A. And the mass is 900 kilograms. Gravity is 9.8 meters per second squared. Again, we've already taken into account that it's a vector, so you don't need to say that it's negative. We already took that into account. And then you subtract the acceleration, which is 1.30 meters per second squared. Okay? Remember, meters per second squared is the same as newtons per kilogram, and newtons per kilogram times kilograms is just newtons, which leaves us with newtons in the final answer, and newtons is a unit for force, so we're definitely on the right track here. So if you plug that into your calculator, you're going to get Ft equals something relatively large, 7,650 newtons. Okay, it's positive. What does that mean? It means that the tension is acting up, and that totally makes sense. Okay, so that's how you write this out. Let's do another one. Okay, we're going to do 5 examples in total, and hopefully by the end you should have a good idea of how to do these applied force and tension problems, because you have a bunch of them to do. Okay, so let's say we have an object that has a mass of 25 kilograms. The mass equals 25.0 kilograms. And it's pushed along a horizontal surface with a force of 95 newtons. Okay, so this force that I'm applying to the block, Okay, I'm pushing it. I'm applying this force. This time I'm going to call it FAP. Okay, you can call it FT, but it just seems more logical to call it F applied because I'm pushing in this case. And FAP equals 95.0 newtons. What else is happening? There's a force of friction of 50 newtons. Okay, force of friction equals 50.0 newtons. And let's find the acceleration of the object. Okay, so A equals what we're looking for. So again, let's draw a free body diagram. Our object is a box. Here's the center of it. And obviously, there's a force of gravity, which is acting down. Okay, force of gravity. We can draw in here. This is positive. This is positive. It's on a surface. Okay, so if you picture this, let's say it's on like some level cement. It's on freshly paved cement on Columbia Ave. And so the normal force is perpendicular to that nice fresh cement. Okay, so it's acting straight up. We're pushing on this box. Okay, so we're applying a force. We're going to apply it that way. And so we also have friction. Friction resists the direction that we're pushing on, so that means that friction is acting in the opposite direction. Okay, so we've got gravity, applied force, normal force, and force of friction. What we want to find out is, what is the acceleration? Well, again, we want to draw in our acceleration. I'm thinking it's going to accelerate that way because that's the direction we're pushing it. Okay, so we've decided on convention. Up is going to be positive, right is going to be positive. If you look at this box, we don't really care what's happening for the normal force and the gravity because we're pushing it horizontally. We're only looking at left to right this time. In the last question with the elevator, we didn't care about left and right. This one, we only care about left and right, and up and down doesn't really matter. So we're going to do the same thing. We're going to say F net equals the sum of the forces. And if you want to be totally correct, now we're looking at it in the x direction, right, horizontally. Okay? And F net is always MA. Okay, and these are all vectors. So F net equals sum of the forces in the x direction equals mass times acceleration. And acceleration is what we're solving for. Let's make one giant equation that we can solve because it's going to make it easier for you. And also we'll get rid of all these hats because we'll just look here at what direction everything is moving in. So, or is being applied in. Okay, so first of all, let's do MA. Okay, the acceleration is to the right. Right is going to be positive, so this is going to be MA. MA equals F net, which equals sum of the x forces. So let's sum the forces in the x direction. Force applied, it's acting right, so it's positive. We're going to go FAP. Force of friction is acting left, so it's going to be negative FF. Okay, I don't have any hats on here because I'm taking into account these vectors with their signs. Positive, positive, negative. Now we're solving for A. So A, we just divide each side by M. So FAP minus FF divided by M will give us our acceleration. And then whatever, if it's positive, it's going to the right, and if it's negative, it's going to the left. Okay, so F applied was given to us. It's 95 newtons, 95.0 newtons. Force of friction, it was given to us, 50.0 newtons. Mass, this object happens to weigh 25.0 kilograms. Okay, so that means you've got 45 newtons divided by 25 kilograms. If you plug that into your calculator, you should get 1.80 newtons per kilogram. And we know that newtons per kilogram is the same as meters per second squared, right? Because a newton is a kilogram times a meter divided by a second squared. So there you have it. The value is positive. It's acting to the right. That's how we drew it. Everything works out. Bingo, bango. Next question. Let's say we have a 3 kilogram object. It's thrown vertically upward with a force of 55 newtons. Okay, we're throwing it up with a force of 55 newtons. So I'm going to call that FAP. The applied force is 55 newtons. And we've also got the mass, which is 3 kilograms. So let's just say it's like a heavy baseball. And we want to know what's the acceleration of the object while the force is applied to it. We know from kinematics that things are going to change quite quickly, right? But that's why they specifically say, what's the acceleration of the object while the force is applied to it? Okay, so we're going to look at it in an instant in time. So we're going to draw this free body diagram during an instant in time. So we're looking for acceleration. Free body diagram. I probably should have drawn a circle there because this is a heavy baseball. But anyway, this is the heavy baseball. Here's the center. What's happening to this thing? It has a mass, so it has a force of gravity. And we throw it upward with our applied force. Okay? Over here, we're going to say up is positive. We're going to say right is positive. Wow, that's wonky. And we're going to get our beautiful equation, which is F net equals sum of the forces. In this case, we only care about the y direction, equals ma. And those are all vectors. So this is one of those things where you can choose what direction you want to put the acceleration in, where you think the acceleration is going to go. And if it happens to be complicated and you work it all out and it ends up being that the acceleration was in the other direction, that's perfectly fine. You'll just get an answer for A and it'll be negative, which means that when you drew it in here saying, oh, I think it's positive, well, it was actually going the other direction. That's the beauty about vectors and about using up as positive and right as positive, is because you'll still get the right magnitude, you'll just get the wrong direction, but that's okay because you can switch it around at the end. So it always works out. So I'm going to say that it's going up because, well, I'm applying my force up, right? So I'm assuming that this ball is being thrown upward because that's what it said. So let's figure this one out. MA, okay? Like I just said, A is going up, so A is going to be positive. So M times A, okay? Again, don't need the hat. A is positive. I'm taking into account the vectors with my directions, positive, negative. Now let's look at F net, okay, which is sum of the y forces. So I've got F applied, which is positive because it's going up, F app, and Fg, which is acting downwards, negative Fg. Okay, and again, just like the last question, we're looking for acceleration. So acceleration equals F app minus Fg, and we divide both sides by m to get rid of that m over there, and that is the equation that we're solving for. Okay, so our applied force minus force of gravity divided by mass will give us our acceleration. So our applied force is given to us, it's 55 newtons. Force of gravity isn't given to us. In the last case they gave us force of friction, so that was really easy. This one's just one step more complicated, but not really, because force of gravity, we all know, is just mass times gravity, right? You should all know that. So I'm going to rewrite this equation to make sure that everything is written down. F app minus Fg is mg, and then we're going to divide that all by m. Okay, so let's put in some numbers. F app, 55 newtons, minus the mass, 3.0 kilograms, times the magnitude for gravity, 9.8 newtons per kilogram, all divided by mass, 3.0 kilograms. Okay, you always want to check your units. I can't stress that enough, actually. Newtons, these kilograms cancel newtons, so you're going to have newtons on the top. On the bottom, you're going to have kilograms. Newtons divided by kilograms is going to give you the same thing as meters per second squared, which is acceleration, so this thing works out. It's really important to check your units. 55 newtons minus, that's roughly 30. So it's going to be 25 divided by 3 approximately. If you plug everything into your calculator appropriately, you're going to get 8.5 meters per second squared. 8.5, well, actually you're going to get 8.5 newtons per kilogram, and we know that that's the same as 8.5 meters per second squared. Okay, we get a positive value. Positive means that we're going up, and that's how we drew it. It was a giveaway because it told us that this object was being thrown upward. But everything works out, and so that's the answer. Okay, let's do the next question. We're slowly going to get a little bit more complicated, and as you might have guessed, we're obviously going to throw in some angles there because we like them. An object that has a mass of 45 kilograms, mass equals 45.0 kilograms, is pulled along a horizontal surface by a rope that makes an angle of 32 degrees with the horizontal. You know what? I'm going to draw the free body diagram first, and then we'll fill in the information. Okay, so there's the center. It's pulled along a horizontal surface. So I'm going to draw it in there. Oh, that's pretty good. And I just said it by a rope that makes an angle of 32 degrees with the horizontal. So here this thing is parallel to the floor. 32 degrees is something like that. We'll draw it in. 32 degrees. This is the force applied. I'm just going to use applied. We're pulling it, so it might just make as much sense for you to say Ft for tension. Again, they're the same thing. It's always going to work out. It's just what you want to use. Okay, so F applied, 32 degrees from the horizontal. What else is happening here? Obviously it has a mass, so there's a force of gravity. It's on a horizontal surface. The normal force is always going to be perpendicular to that. You know what else it gives us? A force of friction. A force of friction which equals 50.0 newtons. The force of friction acts opposite to the force that you're applying. Okay, so we're pulling it this way, which means the force of friction is going to act that way. The tension of the rope is 95 newtons, so F, I'm calling it applied. I probably should have used tension, but again, it's going to work out. 95.0 newtons. What is the magnitude of acceleration of the object? So we want to find acceleration, just like in the last two. Okay, this information that we've written down covers everything. The free body diagram also adds in that angle, and then we have what we're looking for, so that's a nice setup. We also want to add up is positive, right is positive. Okay, so we're looking for acceleration. Again, always, F net equals the sum of the forces. And that equals mass times acceleration. Okay. You could go crazy here and actually figure out what the Fn is and the Fg is, but this thing is only going to accelerate along the floor. It's only going to get dragged along the floor, which means the acceleration is only going to move, I'm assuming, right, because we're pulling it right. Okay, so we really only care for this question about the forces in the x direction, okay? So the sum of the forces in the x direction are what we're going to look at for this question. And then if you wanted to, you could look at it in the y if you wanted to, and that would be sum of the Fy equals ma. As a little aside, a little enrichment for you, what's the acceleration in the y direction? I'll give you 1, 2, 3 seconds. It's 0. There's no acceleration in the y direction. This box is not moving up or down. It's not moving up or down. It's only moving right. Okay? So you could have figured out the ones in the y direction, but we don't have time for that. So let's figure out, we're calling A positive, so let's do MA, and then we're going to sum our forces. Negative, force of friction is negative, so negative force of friction. And then we're going to do plus force applied in the x direction. Okay? The only part of this force that's actually making this move is the force in the x direction. Okay? If I wanted to draw that there, I'd put in this arrow here. And this guy, oh, that's terrible. There, now it's beautiful. F applied in the x direction. Okay? And we know how to figure that out. F applied in the x direction. I'll give you 3 seconds to figure out what that is. F applied in the x direction. Quick. It's F applied times cos 32 degrees. Okay, if you can't figure that one out, then you need to go back and do a little bit of your vectors. Here's the angle. This is theta. This is x. This is the hypotenuse. If this is theta, this is opposite. This is adjacent. What uses adjacent and hypotenuse? SOHCAHTOA, it's cos. Okay, so F applied in the x direction, sorry, is F applied times cos 32 degrees. So let's rewrite this. MA equals negative FF plus F applied times cos 32 degrees. And that's all we need. We're looking for A. This is taking into account our vectors. We'll just divide each side by m. A equals, and I'll rewrite this a little more pretty, which is FF cos 32 degrees minus FF all divided by your mass. Okay? And we have all these values. F applied is 95.0 newtons times cos of 32 degrees minus force of friction that's given to us. It's 50 newtons, 50.0 newtons. And we're going to divide all of that by the mass of the object, which is 45.0 kilograms. Check your units. We've got newtons minus newtons, good, divided by kilograms, newtons divided by kilograms, meters per second squared, so you're going to get an acceleration. Perfect. If you punch all these numbers into your calculator and figure this out, you're going to come up to an answer of 0.679 newtons per kilogram, which equals 0.679 meters per second squared. We said the acceleration is positive. Positive is to the right. That's the way it's going, and it better be because that's the way we're pulling it. So, beautiful. That one worked as well. Okay, let's punch out the last question. Last example. A 75 kilogram student stands on a bathroom scale on an elevator that is accelerating upward at a rate of 1.00 meters per second squared. What is the reading in newtons on the scale? As a little note, scale reading will be the normal force, which is equivalent to applied tensional force of the cable. So mass equals 75.0 kilograms. Accelerating upward at a rate of 1.00 meters per second squared. Okay. Let's draw this. Oh, and what are we looking for? What is the reading in newtons? Which is going to be Ft, which you have from that little aside. So here's the box for our elevator. Here's the center. Everything's acting from this. It said acceleration is upward. We're doing that. Here is Ft, tension in the cable, reading on the bathroom scale. This is Fg, force of gravity. Again, F net equals sum of the forces equals mass times acceleration. These are all vectors. Up is positive, right is positive. In this case, we're only looking at up and down, which means we're really only looking at the y direction. Okay, so let's do that. We're looking for Ft. Okay, so let's look at MA. A is going up, A is positive, so we're going to go M times A equals. Now we need sum of the forces in the y direction. Ft is positive, so it's positive Ft. Fg is going down, so it's negative Fg. Fg, we all know, is mass times gravity. So Ma equals Ft minus mass times gravity. Okay, so that means Ft, if we rearrange this, equals mass times acceleration plus mass times gravity. And we can also simplify that because we can factor out the m's. You don't have to, but it looks prettier and it involves less calculator use, which is always a good thing. Now let's punch in the numbers. 75 kilograms times acceleration, which is 1.00 meters per second squared, plus, actually, you know what? I'm not going to write plus. I'm going to convert those units to newtons per kilogram because I can do it this way. Times newtons second squared kilogram meter. Right? 1 newton is a kilogram meter per second squared. and I just flipped it around. Second squareds cancel, the meters cancel. We're left with newtons, okay? Plus gravity, which is 9.8 newtons per kilogram. We know that. Okay, so that's going to be 75 times 10.8, and if you punch that into your calculator, you're going to come up with an answer of 810. Let's check our units. Newtons per kilogram, newtons per kilogram. Those add up. Newtons per kilogram times kilogram leaves us with newtons. Newtons is a force, which is beautiful. We get Ft equals 810 newtons. That's positive. That's good. It's acting up. Everything works out. So if a 75 kilogram person stood on a bathroom scale in an elevator and that elevator was accelerating upward, they would actually show a reading on the scale of 810 newtons. They would show a reading on the scale of greater than what they would if they were standing on the elevator and the elevator wasn't moving. So I'm going to leave you with, think about what would the reading be on the bathroom scale if you're standing on a bathroom scale on an elevator and the elevator is moving down. Think about it. Thank you.